All right, let's get started. So this is my procedural and conceptual assignment on the division of rational numbers. Let's break that down though into, okay, what does division mean? So division is the process of dividing something into parts. That is true. So let's say we have a rectangle, for example. And let's say this rectangle is 10 inches long. And if I wanted to break that into parts, I could break it up so that we have a 3-inch piece, maybe a 2-inch piece, a 1-inch piece, and we also need a 4-inch piece. So this is division, is breaking something up into parts, but when you're talking about math, we have to divide whatever we're working with into equal parts, and there's a reason for that. So with the mathematical operations of addition, subtraction, multiplication, and division, we use those to manipulate equations. Now, equations are statements of equality between two math expressions. And the key word to take from that is equality. Now, the best way I can represent an equation is with the seesaw. Hopefully, all of you know what a seesaw is. A prime example. So we have two little piggies sitting on both sides of the seesaw. I'm assuming they're someone's piggy banks, and they have the same amount of money in them. So if the two piggy banks are the same size, then they will balance the seesaw. So we can assume that the middle portion of the seesaw is going to be the equal sign. This piggy equals that piggy. Now, the mathematical expressions, they're going to be paired together, just like the pigs are, where when you're playing on a seesaw, you need two people. So since we have 4 mathematical expressions, we'll pair 2 together and the other 2 together. Now, the first 2 that go together are going to be addition and subtraction. So let's say if we have an equation such that one is heavy on the addition, like we could say if x plus 5 equals 9. In order to balance that equation, we would have to subtract 5 in order to set it equal. So addition and subtraction are paired together in this mathematical expression. We have to subtract 5, we have to subtract 5. And likewise, if we went to another seesaw that uses multiplication and division, let's say multiplication was heavy on one side, and our equation was 4x equals 16, the only way to balance that equation would be to divide both sides in order for it to equal. So we would divide by 4, we would divide by 4. So when we have an equation and we want to balance the seesaw, we have to remember that these two pairs will be playing together on the seesaw. Now, with division, division can be represented multiple ways. So in a question, you may be given a word problem that says, how would you represent 12 divided by 3? Or how would you divide 15 by 5? They'll give you a word problem. So there are 3 ways you can do 12 divided by 3. You can write it 12 divided by 3. Or you can do it 12 divided by 3. You see, you have 3 different ways. The one that we're going to focus on is this one. You see that in most homeworks, quizzes, tests, and so on and so forth. Now, the form that this one is in is we have the numerator on top and the denominator on bottom. Now pay close attention to that because you'll see that throughout the entire paper. But now the next example is, okay, well, how do you actually solve this problem? How do you solve 12 divided by 3? Now, let's go to the next page. All right, so when solving this problem, you most likely won't see it as easy as this, where the larger numbers on top, the small numbers on bottom. So for this example, 12 divided by 3, if you guys know your multiplication table, it's going to be 4. But the majority of the time, most of the fractions that you will see will be in the form of where the small number is on top and the large number is on the bottom. So let's look at an example of one of those. So fractions are going to be part of a whole. So with the numerator being on top and the denominator being on bottom, numerator, denominator. So the numerator will be the part. It will be a section of the whole piece, where the denominator will be the whole. Now the whole can change depending on what your whole is. It could be a circle, a square, a number, but the whole will be the larger number, the part will be the small number. So for example, if our whole is one circle and we wanted to divide it into 2 equal parts, this half of the circle is 1 and there are 2 total pieces. In this example, we have 3 equal parts. The green shaded part is the one part that you have, and the other 2 are unshaded. So there's a total of 3 parts, or 3 total pieces to make the whole. And you can do this so on and so forth until you get a larger number in the denominator, and the 1 will normally stay the same in the numerator. Now, let me give you an example that you guys can all relate to. Pizza. I'm hungry as of right now. I'll probably do pizza after this, but let's say your parents ordered pizza and they let you eat 1 piece. And they were to ask you, well, how much of the pizza did you eat? You could say, well, I had 1/8 of the pizza. I ate 1 slice. There's 8 slices total. And you only ate 1. I'll say 8. Only 1. So this is an example of the part that you ate and the total that came with the pizza, 8 total pieces. So I want you guys to apply this concept to the division of whole numbers. Now, whole numbers include 1, 2, 3, 4, 5, 6, and so on and so forth. I guess you can go all the way up to infinity or a million if you want to. But they pretty much include counting numbers. So let's look at the next page. Oh, we missed something. Hold on. Let's scroll down. There we go. Let's scroll down. All right, so how do we understand the division of various subsets of rational numbers? Basically, fractions, only no decimals, and then what are the procedures and what are the conceptual underpinnings for those procedures? So I want to give you guys an example of a division problem dealing with whole numbers where we're going to have, let's see, I'll do 252 divided by 3. So like I said, there are multiple ways you can write this. We're actually going to write this in one of the other ways that I expressed from above so that we can actually solve it. So I'm going to do 252 divided by 3. I'm going to write it like this because I'm going to show you guys how addition, subtraction, and multiplication and division are all related. So hopefully all of you guys know your multiplication tables. There are various ways you can solve this problem, but I like this way because it breaks down large numbers. So let's do this. We're going to find out how many times 3 goes into 252. So I like to think of my 3 multiplication tables. We're going to have 3, 6, 9, 12, 15, 18, 21, 24, 27, and so on and so forth. So if you know your basic multiplication table, you can solve pretty much any high level or higher level division problem. So let's do this. Let's say we know that 3 times 8 is 24, and we're going to do this. We're going to subtract 240 from 252. So the question is, what 2 numbers multiply together to give you 24 when you use 3? So we know that's going to be 8. So that's the multiplication aspect of it. When I subtract, I'm going to get 12. Now, this was a problem we did earlier. So how many times does 3 go into 12? We know it goes into it 4 times. And 12 minus 12 is 0. So we're going to go back up and put in, we're going to add 4. So 3 times 84 will give us a multiple of 252. So I want you guys to remember this process because we're going to use it on the next couple of examples. And normally I would give my students several examples like this with numbers so they get practice and they're familiar with dividing into larger numbers. So let's look at the next page. All right, so now we're going to be talking about the division of whole numbers. So let's look at a practice problem, practice word problem. So it says, Grace has 72 flowers growing in her yard. She wants to take all 72 flowers to her local retirement home, but can only put 6 flowers in a vase. How many vases will she need in order to carry pretty much all 72 flowers to the retirement home? So let's think of this as an equation. So we have 72 total flowers. She can put 6 in a vase, and we need to find the total number of vases that can carry all 72 flowers. This is almost like a math equation. So we're going to do, draw a squiggly line. We'll do the number of vases times 6 flowers per vase. And we want that to equal the total of the 72 flowers. We're out of space. So remember, think back to the seesaw where the pairs that came together were multiplication and division. So imagine the seesaw being right here and it's trying to balance on here. So we have multiplication on this side and just a number on this side. So if the side is heavy with multiplication, we need to balance this with division. So we're going to do the number of vases times 6 flowers equals 72. We're going to want the number of vases on one side of the equal sign, so we'll divide both sides by 6 flowers, divide both sides by 6 flowers. Oh, nice space. And what we eventually get is the number of vases is going to equal 72 divided by 6. And then this becomes just a division problem like we did previously on the last page. And this is ultimately going to equal 12. So we need 12 vases to carry all 72 flowers for the retirement home. let's look at another example. Oh. All right, so Jason wants to buy a new pair of shoes that cost $120. It might be Jordan, I don't know. He has a part-time job cutting lawns on the weekends. He charges his customers $15 per lawn. How many lawns will he need to cut to have enough money to buy the shoe that he wants? So we'll treat this example just like we did the previous one, where we're going to set it up with an equation. So we have he charges $15 per lawn. And we need to find out how many lawns he has to cut in order to get $120. So remember, this is like another seesaw problem. We have seesaw right here. Now, this side of the seesaw is heavy with multiplication. So in order to balance the seesaw out, we're going to divide both sides. So we're going to divide both sides by $15 per lawn. Divide by $15 per lawn. And we'll get the number of lawns will equal 120 divided by 15. And that again is another division problem. And we get the number of lawns is going to equal 8. So we have to cut 8 lawns in order to get the $120 for his pair of shoes. All right, we have another example. So now this example is going to focus on, okay, is the division closed with respect to whole numbers? So let's read the problem. It says, Kendrick has 3 dogs and he takes them for a walk one afternoon. The humidity suddenly increases and he wants to provide enough water for all 3 dogs to stay hydrated. He brought a 1-liter bottle of water for all of them. How much water does each of Kendrick's dogs get? So remember, the number that we're dealing with is he has 3 dogs. He has 1 bottle of water. And they have to divide that so that they get the same amount equally. So we'll do 1 bottle divided by 3 dogs. Can't stop. Now, these are both whole numbers. We're dealing with 1 and 3. But in this case, the numerator is smaller than the denominator. So we're not going to get a nice number when you do divide. Now, remember, whole numbers, they have to be countable. 1, 2, 3, 4. So you can't get decimals. So the answer you'll get is 1/3. And that's not a whole number. So division is going to be closed with respect to the whole numbers because all the numbers provided in the equation have to be a whole number. 1/3 is not. All right, the next section, we're going to deal with integers. So this was a rather long problem. I think my word problem got longer and longer as I made them up. So it says, Ryan built a snowman in his front yard after a terrible snowstorm. He was so impressed that he measured the height. Each day it got shorter and shorter, but he wanted to find the average of how fast it has melted over the past 4 days. So day 1, it was 60 inches tall. Day 2, it was 58 inches tall. Day 3, it was 54. And day 4, it was 48. And on day 5, it was only 40 inches tall. So pretty much the snowman was melting the warmer it got outside. So we're going to be dealing with negative numbers in this example. So let's see, let's make a little chart. How much space we have. So we can say day 1, it was 60 inches tall. Day 2, it lost 2 inches, so we can say -2. Day 3, it was 54, so it lost 4 inches. Day 4, it was 48, that's -6. And day 5, it was 40 inches, so it lost 8 inches. So now in this problem, they're asking for the average. Find the average of how fast it has melted over the past 4 days. So we're talking about this day, this day, this day, and this day. Now an average is going to be equal to a sum divided by the total. So what we're going to do is we're going to add up the numbers for these 4 days and divide it by the total number of days. So in this example, our average is going to equal, let's see, 2, 4, 6, 8, 10. 10 and 10, so that's 20. So it melted a total of 20 inches in over 4 days. So the average per day would be -5 inches for that example. So remember, integers are positive whole numbers and negative whole numbers, and it also includes 0. You guys know numbers, I'm sorry. I apologize. All right, so this example, it says Marissa is driving home from a long day at work. She is hungry and decides to order a pizza with 12 slices. I think that's Lido's, I don't know, I haven't been there before. But she invites her friend Annie so they can catch up and binge watch TV. She gets home, greets her roommate and says, I ordered pizza for dinner. Yay. She hears the doorbell, it's Annie, and she brought another friend, Sarah. Marissa welcomes Annie and Sarah, but is not sure how to divide the pizza between everyone. How much pizza will each person get? All right, so we need to find out how much pizza will each person get. Basically, how many slices will they get? So let's come up with an equation again to figure that out. So we'll have let's say the number of slices per person, number of slices PP, times the number of people. And it's going to equal the total number of slices in the box. We'll have 12 slices. So again, this is our seesaw equation where we have seesaw trying this way. The seesaw is heavy on this side with multiplication. So we need to do the opposite. We need to do division. So we're going to divide both sides by the number of people. So I'll do, let's see how many. There's Marissa, there's Annie, there's Sarah, and there's the roommate. So we have a total of 4 people. So divided by 4 people, divided by 4 people. So we'll get the number of slices per person. We get 12 divided by 4. And that'll give us 3. So that is also an integer. So we are good on that. All right, so this next example is the question asking about, is division closed with respect to the integers? So let's say we have the same problem where Marissa has a friend over for pizza. We're going to binge watching TV, Netflix probably. So let's say if Marissa's roommate invites her friend to join them how much pizza would each person get? So if we use the same equation, if we use the number of slices per person times the number of people, it's still going to equal 12 slices. Now we added a person, so we're going to change the number of people. So we'll have the seesaw. Since this side is heavy multiplication, we need division. So we have a total of 5 people now. We have a total of 5 people. So the number of slices per person is going to equal 12 divided by 5. Now this is not an integer. We're going to get 2.5. So this example does not work. We use an integer 12, we use an integer 5, but the answer is not an integer. All right, so the last section, let's look at the division of rational numbers. Now, before I even start these examples, I want to give you a couple examples of, this will probably be like a warm-up, using rational numbers. So know what fractions are like with whole numbers and integers. Now, what if we were to apply those to a set? Meaning, the question is asking, what is 1/2 of 12? So in order to do these type of problems, you do need to know how to multiply fractions. So we know that 1/2 is this one, and we know that 12 is this one. So what is 1/2 of 12? You have to be able to turn a whole number into a fraction in order to multiply it. So let's change this. So we'll do 1/2 times 12 over 1. Anything divided by 1 is going to be itself. So now that we have two fractions, we can multiply across the top, multiply across the bottom. So we'll get 12 divided by 2. And that's a lot easier to deal with. And this one we will get 6. Let's do another example. So let's say, what is 1/3 of 15? So we need to follow the same process, the same procedures. So we need to turn 15 into a fraction times 15 divided by 1. We're going to multiply across the top, multiply across the bottom. So we get 15 divided by 3, and we get 5. A very nice, simple problem. Let's do one more, just for practice. So we have, what is 1/4 of 28? Same thing, same step. (28 over 1) is the same thing as 28. Multiply across the top, 4, and if you remember your multiplication tables, that's 7. All right, so I'm going to use these in the next couple of examples, so make sure you don't forget it. If you don't use it, you lose it. Like I said, my examples get longer and longer. I'm sorry. All right, so one weekend you go to a friend's birthday party, and as you are leaving, they ask you to take some food home because there was so much food left over. You've decided you'll take one of the pies. However, each pie has been sampled, so there isn't a full pie available. You like the blueberry pie, so you grab the box and check how much is left. There are 5/8 remaining, and you are happy with your choice. As you go home and reach your driveway, you told your neighbor about this party and promised to bring back something. So you stop by their house and drop off half the pie. You get home and enjoy the last slice. What fraction of the pie did you get to enjoy? So this is, I feel, a multi-step problem. We have a couple couple fractions. We have 5/8. We have half. It should be 1/2. 1/2 of the pie. And they want to know how much did you enjoy afterwards. So we have a fraction. We have we have 5/8 of the original pie, and we also have 1/2 of the original pie. And they want to know, okay, well, how much is left over now? So for this example, so you took 5/8 of the original pie home. So the original pie had one whole pie in it. So this is a simple multiplication problem. This is just 5/8. Anything times 1 is itself. So you gave half of what you had to your neighbor. So now we're going to do 1/2 of 5/8. So they want to know, after we multiply this together, they should give us the remaining part of the pie. So we're going to multiply across the top, multiply across the bottom, so we get 5/16. So this is the fraction of the pie that you enjoy. You get 5/16 of the pie. Very nice, very nice. Let's look at the next example. I guess it'll get longer and longer. So yeah, this one is going to be, I'll call this a 4 or 5 step problem. So I feel like you guys can relate to this one since you have your phones out in school all the time. So this is a problem that you guys can be able to solve easily. So it says, Zoe gets to school and realizes she didn't charge her phone all the way. She is worried because when the battery on her phone drops below 10%, it will turn off automatically to save power. Her phone is on 80% and she needs enough to get through 4 classes. Her first class, she used 1/4 of her battery. Her second class, she used 1/4 of her battery. Her third class, she used 1/3 of her battery. And her last class, she used 1/2 of her battery. So the question is, will Zoe's battery have enough life to stay on during her last period? So let's do some math. So we have percentages here and here. We have some fractions, 1/4, 1/4, 1/3, and 1/2. So the first thing we need to do is let's convert the percentages into a fraction. So here's a quick hint. So 80% of your phone is going to be the same thing as 8/10. That's 80%. There's a fraction. So after her first class, she used 1/4 of her battery. So we can say in the first period, she used 1/4 of her battery, which is already at 80%. And if we multiply this out, we're going to get 8 divided by 40. So let's reduce that down. This is going to be equal to 1/5. So now we're going to need to subtract 1/5 of the battery from the original amount. So 1/5 is also going to be equal to 20%. So to make it easy, we can do 80% minus 20%. We get 60%. And now I want to convert this back to a fraction so we can multiply during the second period. So this is going to be 6 over 10. Now let me change color for the next period. All right, so actually I'll call it third period. It'll be an odd day. So on her next period, she used, or let's see, her second class, she used 1/4. So she did 1/4 of her current battery, which is 6/10. We're going to multiply across the top, multiply across the bottom. We'll reduce that so we get 3 over 20. And if we turn that into a percent, I'm going to cheat and use my calculator. My brain hurts. It's equal to 15%. So now we have to subtract her current battery minus 15%. So we'll do 60% minus 15%. So we get 45%. And if I convert that back to a fraction, I'm going to get 9 over 20. So now let me change colors for the next period. So the next period will be fifth period. So in fifth period, she used, let's see, her third class, she used 1/3 of her battery. So we use 1/3 now. So 1/3 of 9 over 20 is going to equal 9 over 60. And that's also going to equal 3 over 20 after you reduce it. So 3 over 20 is also 15%. So we'll do, where is it? 45% minus 15%. So now we're down to 30%. So we're getting close to that 10% to where her phone's going to cut off. So now her last class, we'll call this 7th period. Do or die. So in 7th period, she used 1/2 of her remaining battery. That's a lot. So we have 1/2 times for 30%, which is 3 over 10. If I multiply across the top, I get 3 divided by 20. And we've seen that in the previous 3 problems, 3 over 20, 3 over 20, and so on and so forth. So this is going to be equal to 15%. So this is what her battery is left with after using her phone throughout the entire day, 15%. So to answer the question, will her phone shut off? Nope. Still good. All right. All right, so the very last page. So in my conclusion, I want to answer these last 2 questions. The third one asks, what would it mean to say that someone is procedurally fluent when working with the division of rational numbers? And to me, that means a student, when given a formula or given a process or procedure, they can pretty much just spit it back at you. So if they had an example of, let's say they had, I don't know, 5 divided by 8. We have 2 whole numbers. Or if they could solve -1 divided by 2. We have an integer and a whole number. Or if they had 3/5 divided by 1/8. So if you give them a simple problem like that and they're able to solve it with no problems, to me, that's what it means to be procedurally fluent. But that is just the basis of learning. Like, that's just regurgitating what you learned in class. But the next question to me is the most important one. What would it mean to say that someone has a conceptual understanding of the division of rational numbers? Now, to me, that's the next level type of understanding where, okay, not only do you know how to follow the procedures to answer these types of questions, but to have a conceptual understanding means, to me, two things. It means you can teach other people these processes to solve this problem, this problem, this problem, and give me an answer, but you can apply what you learn to word problems and critically think and apply what you learn to solve almost any real world type of problem. So the conceptual understanding is my true definition of learning a concept, of learning a topic. So thank you guys. I think I reached my limit, probably doubled it. I think it's supposed to be like 30 minutes long. I'm sorry. I had to give you the full take on division of rational numbers.